I signed up to this workshop last year, I did not know that I would have to move my family to Colorado 10 months. Actually, during this month. So I asked Matthew or Keith whether they would be willing to replace me here. Neither one of them had time for something. So, but that helped me out by giving me this CSM tutorial on the biogeochemistry module in CCSM. The purpose of this is to give you an introduction about what are the components of the biogeochemistry model that we have. CESM. CESM is the community Earth system model. Probably one of the top 5 models in the world at this deep. It has as much in there as you can do right now. So I think by this definition it fits Hesse's definition of a GCM. It has a 100-kilometer resolution. A lot of the IPCC simulations are done with this model. It also has a biogeochemistry. It also has a biogeochemistry component, which I'll discuss today. Keith Lindsay is the main developer of this model. This model, there are about 50 people that are currently working in maintaining and developing the model code. Meteorologists, physicists, numerical scientists, computer scientists, and mathematicians. And they stay in close collaboration with several hundred university scientists. So the idea is this whole CESM project, it is based in Boulder, Colorado. But the idea is that this is an open source project. So different parts of the communities come to their best ideas and think this is something that we should represent in the platform. And we will take these components then, after it has been validated by the community, and make this part of our Earth system model. In this particular case, Keith Lindsay is our connection to the marine biology community. He's a applied mathematician, but he's able to translate the occasionally fuzzy ideas coming out of the marine biology community to numerical code, and then translate this into something that is representable by a computer. This is a major challenge because there are many interesting ideas out there, but they have to put into numbers or lines. I'm only just in working in the bit of biogeochemistry is been pushed for years by Markus to get into this carbon cycle modeling in fisheries. And I started working on the glacial cycle of biogeochemistry. This is something that Hesse discussed briefly. This is how I got into this. So I'm a user of this biogeochemistry model a little bit, but it's really Keith Lindsay who's doing the main development, who brings the ideas of the university communities into this model. And I think here's the first block, and I'd like to highlight you and several blocks where you as a community or the growing community could connect with us. We only have 1 or 2 marine biologists in our institute, but the idea is to bring ideas, relatively developed ideas from the university into this model and make it part of the model. This is a two-way interaction. We can do our own. The communities have to decide those are important parts. These are where we support the developments. The outline for today is, again, the goal is to show you what is in there, where you as a community can connect. We want to host the fisheries, these are the things we can help you with, and those are the blocks where you can connect with us. With this brief motivation, then I'll show you some large-scale biochemical distributions, and then how we try to model them. And there will be some brief model skill assessment, what are the variables we actually can reproduce, where are the shortcomings, where you should not ever trust the model, at least in our model. You can't trust our model, many other models are probably not trustworthy either. And then I give some presentation of the other model, carbon cycle. This is probably the highest level of biogeochemistry, higher trophic levels. It's in its infancy. Who and particularly here I did some work on fisheries, where we connect fish models, the output of this model. But again, this is very much in the infancy. But it is possible. I mean, developments are underway. I would encourage you strongly to continue this. So we don't have to talk too much about this. As we saw already over the last 1,000 years, you see that the CO2 concentration was rather steady, to the point that it's so steady that you wonder, do we have to try to understand this at all? There's much going on. Already we showed there some large variations. took off over the last 150 years, pretty soon after the invention of the steam engine. The extent we were too worried about it. And I had a discussion with somebody recently who said, well, we don't have to understand the natural carbon cycle, because clearly what we're doing here with the carbon cycle is such a large signal, it dwarfs anything natural in the system. But I think it comes down to the idea of the model validation. So at some point you have to assess, does the model represent the real world at all before you go into the deviations. So there's some value looking at the natural carbon cycle, which would be the first part of this year. So in the first step would be in the model represent deforestation and the fossil fuel emissions. But also where are the sources and sinks, natural sources and sinks of atmospheric CO2. You see there were large changes over the last 100 years again, the takeover of the fossil fuel emissions. But even until 1950 you can see that deforestation was a large part of the anthropogenic CO2 contribution. One of the main research questions right now is that we are trying to address with the model. This is actually where the funding comes from for this model. Is not only to deliver to the community a climate model that represents the physical parts like temperature and precipitation, and to look at this in the future, what effect does CO2 have, but also identify the sinks of the atmosphere CO2. What we have a fairly good understanding about the amount of CO2 in the atmosphere. What you see here already, much of what we know is what is taken up in the ocean comes from models and comes from assumptions and theories. And the land is completely open, this is really just determined zero. So we have very little understanding about the details of the sinks and the mechanisms of the atmosphere. This is an active research project. We'll come back to the question of the natural carbon cycle. Why is it interesting to start understanding the natural carbon cycle first? And this is shown here, and Casey showed this briefly before as well. This is the atmosphere CO2 concentration and the temperature over the last 400,000 years. The red line is the temperature. You see the characteristic slow cooling and sudden warming of the atmosphere of the Earth every 100,000 years or so. And the blue line is the atmospheric CO2 concentration, which follows it closely. And the emphasis is here really on the following. The CO2 does follow the temperature. There have been recently very high resolution measurements done here over the last declassification. And it became very clear now, and I think this discussion is mostly settled that the temperature is eating the atmosphere of CO2. So for Earth's history, at least in this one well-recorded event, Earth first started to warm, and then the atmosphere of CO2 started to increase. So its temperature is leading the CO2. This is very different than the story that the community is telling our society that the CO2 is leading the temperature. This may still be true, but I think as a community we really have to explain why it has been different during the ice ages to maintain any credibility. So for us, IMBER, this is a major focus of research to understand the natural CO2 or carbon cycle. We have not only oceanographers, but also meteorologists, chemists, and terrestrial scientists working on this. But I focus mostly on the ocean today, for the marine biology in the ocean. A small primer here on carbon chemistry in seawater. We have CO2 gas form in the atmosphere. It is dissolved in the ocean, combines with water, and the trick is here that as it combines with water, it's up in different carbonate ions and hydrogen ions. Because of the split up, the ocean is able to take up more CO2 than it would be otherwise. It takes a while before it's saturated. That makes the ocean a very efficient sink of the ocean. And you see this here that because it's a very efficient sink, most of the ocean, the world's carbon is actually contained in the ocean. So in a longer time scale, the larger amplitudes, the ocean is really dominating the atmosphere, the atmosphere of the Earth's CO2 concentration. So this is the question then is what shall we model? What is the variables that we should be looking at? I mean, platform from ASI that there are numerous variables that might be of interest. We have to limit it ourselves just because of the computing resources. I mean, this is one of the nice things about modeling. You're forced to try to identify the most important processes. We often get that wrong, but at least we have to think about our ranking just because the financial and numerical resources enforce that. This is one of the key variables that we have to verify our biogeochemistry model. This is chlorophyll. This is the chlorophyll concentration from the numerical model. You see is a lot of it's in the observation. Well, sometimes they're so similar, sometimes they're hard to distinguish between the model and the observation. But this is the chlorophyll concentration from the observations. You see the highly productive regions. So this is observed by satellite. It's again, it's a numerical model that connects what you see as long wave emission on the ocean surface, and is then converted into ocean color, and then converted into some interpretation of chlorophyll. So we have to be careful with these interpretations as well, because there's also a numerical model in there. But I think the first approximation it identifies the areas of high biological productivity. So the coastal upland regions here of Peru, India, a lot of here in the Baltic Sea, where we have river outflows that are full of nutrients. It's nice to see here, for example, the Amazon, where the nutrients are delivered by rivers, whereas here those are different dynamical areas where the nutrients are delivered by coastal upland, so you will have deep waters that are rich in nutrients to the surface. And this is a challenge for climate models, because you have to get the river outflow right, as well as the coastal upland regions right. So all the different physical processes have to be in place in an Earth system model to enable, even if you have the perfect biogeochemistry model or the perfect biological model, to enable these models to work well, you have to have a background of a good physical model as well. So this is the challenge. And partly we use this as a challenge because it's already well observed. We have now more than 10 years of satellite data. It covers the whole globe. Most of the variables which would be more desirable are very poorly observed. So it's well observed. So partly we like this drug that goes where it's key at night. So you look where you have light shining rather than where you suspect the key is. This ocean biology is one of the major sinks for carbon in the ocean. As you showed us, we have a biological pump as well as a solubility pump. Solubility pump is straightforward physics and chemistry, whereas plankton also, there's a plankton, the biota acts as a transport means to get the carbon into the deep ocean. And thus, you move it from the surface and the exchange to the atmosphere. If you want to change the atmospheric CO2 concentration, to bury the carbon in the abyssal ocean. So through photosynthesis, you transform the light and the carbon and water into organic matter. This is a fundamental principle. You get some oxygen that is then released to the surface. And as these hydrocarbon dyes, it sinks beneath the ocean surface. So it's usually says the upper 100 meters, the euphoric zone. And there is life below 100 meters, but it does not live directly on sunlight anymore. But it lives to a large extent on stuff that falls from below. So that the undertaker of the system, which returns organic matter and oxygen. So you need the respirates, so you need oxygen to convert this organic matter to support the spouting processes, which then leads to dissolved CO2 and to nutrients again. And these nutrients become extremely important then to feed the phytoplankton again, these upwelling regions. In upwelling regions, you have vertical transport processes that lift the nutrient-rich water from the nutrients, basically from the ancestors, bring it to the surface, where you can feed again these nutrients. Not all of this circles through. Some of this sinks deeper, some of them sinks in the sediment. The sediment in the abyssal ocean, they have time scales of 1,000 years, are a major controlling factor for the atmospheric CO2 because you can remove the CO2 from the surface to the abyss. This is here some observational illustration, these fundamental processes. Again, what we do here is we produce oxygen in organic matter. We remove oxygen below this